process that you sort of create hail high in the really cold and energetic parts of the storm. And when it gets too heavy, it comes down. So you can get lightning, thunder in a snowstorm, and you might not see it, but it's probably happening way up in the cloud, up at the top where it's real cold. So the difference is that anything that's producing hail is probably producing lightning. A snowstorm probably isn't, because it's a gentle kind of super cold thing and the clouds all low to the ground. But, because nothing is fixed, Japan, for some reason, gets an awful lot of winter lightning. I don't know. They do.
I heard you correct when you said earlier that we don't know what propagates like around the globe, right?
Well, we think what I hope I said. We think that this fair weather field that is there is being maintained by thunderstorms all around the globe. So it's like an electrical circuit that's always in action.
Sure.
And if we took away the thunderstorms, it would settle. It wouldn't be there.
What is the probability of the Earth's rotation helping that out?
I don't know.
Earth's magnetic field cutting lines of flux.
Oh, so the Earth's magnetic field travels with near the surface. It's traveling with the Earth, and so it's not causing a shear. And this stuff happens pretty low, actually. Lightning is typically happening between 10 and 30 kilometers up, which is pretty low.
I'm curious to believe if I understood right, the same visual light and how it travels. What's the story about that? Does it mean light traveling through a cloud, for example, or just through space? And that you're looking at how it happens the way, like electrons, for example, in that bolt of light is happening?
Well, what I was looking for was when you get a lightning discharge and the big current flows and it heats up the air, that whole process only lasts, 10 microseconds or something. You might get multiple bursts like that, but each one is, 10 microseconds, 100 microseconds, something slow, or fast, rather, short. And it heats up the air and you get a little burst of light. But when we observe it from a distance, the light lasts up to a millisecond, like 100, 1,000 times as long. Because every little photon of light comes out and it hits a particle of cloud and it deviates and it scatters all over the place, and finally you get something. So a lightning event, when you observe it, you can go look at space station movies of lightning, and you'll see lightning, something seems to happen, and you'll see a little bright spot, and then you'll see the whole cloud glow, because the light slowly sort of diffuses. It's a diffusion process. And so I was curious if I could look at this diffused signal and recover what the original signal was. And the answer is you can't. So.
What is the, for a, I understand it's probably altitude dependent, atmospheric density dependent, but what is the diameter of a lightning strike? Is that 200 meters above the ground? Is it single-digit centimeters?
I think it's
The ionization.
10-ish centimeters, yeah, I think.
So how does the information about what's there on the ground, what's the highest point, how does that information reach the lightning? Is there like some exchange process that's happening before the lightning strikes?
It's just a really good question. There's something happening on these small scales that, and I think what's happening is you get all these little steps, and they're happening in their own little region, and they're oblivious to what's going on in the rest of the cloud. But once you make a connection between charge layers, like the Earth is a huge source of charge or a huge sink of charge, or you've got charge layers in the cloud, once the instant that connection is made, now you've got a channel, and it's communicating in the sense that it's dumping charge in one direction or the other. Up till that moment, it didn't know anything about its environment. It only knew, I don't necessarily think that the cosmic ray seeding is what's going on. I think that it's happening on these super tiny little spatial scales, and when you just get a whole bunch of them, they come together to create this enormous thing.
Have you studied clear air, like clear air discharges after the sun sets and the clouds around? atmosphere flash?
I have not, no. I've heard of this. Is this the green flash like that people say they can see over the ocean?
It
Yeah.
almost looks like there's a lightning bolt somewhere, there should be clouds.
Huh. I haven't seen it. I have heard of it, but I haven't studied it, no.
About a month ago in the paper, there was a map of town with 100 or so lightning strikes. How was that measured?
So I didn't see the map. I'll just guess. I'm good at that. My guess is that we have a number of sensors that we have around town. And so it could have been from our sensors that are measuring radio wave pulses. But also, there's something called the National Lightning Detection Network, and you can buy their data. So anyone who buys their data can make a map of everywhere that lightning happened. So there's multiple data sources out there that somebody could have used to make a map. And they're almost all done the same way. They're almost all some kind of electric field change meter, something that's registering every little change in the electric field.
So this is related to that kind of, I think. So sometimes, say you're watching your weather app and you have the lightning detection thing while you're at it, and you hear nothing, there's no thunder, the storm is still building, but it says lightning just struck less than half a mile from where you are. Is it because those apps are using a detection method that just is looking at the electric field or electromagnetic field, or they're not, or how is it?
So there's lightning with a little L, and then there's lightning with a great big L.
Mm-hmm.
And so these arrays, like the lightning detection network or our sensors or whatever, they're really sensitive, and they pick up a lot of stuff. So there might be lightning, but it's super small, and it might not be enough to make there's thunder, but maybe you can't hear it, or there's light, but it doesn't get out of the cloud, or it could be super small, because there's a lot. And so you just might not, I don't know if the app, I've not seen the app, if it gives you any kind of sense of size.
No, it just says like lightning strikes. I have
So-
like 4 apps so that I can see which one's
Yeah.
telling me which, so
Okay.
which one's right. But
So it depends on just how sensitive the receivers are, and if they're picking up really small stuff, it could be in the cloud, not connecting to ground, and a lot of the sensor arrays don't differentiate between something happening in the cloud and something attaching to ground.
Okay.
So I understand that we get the second highest number of lightning strikes in Hazel's Mountain, with only Florida getting more than we do. Why?
Well, I think it has to do with it gets hot, and we get these convective updrafts. That's true in terms of we get hot spots, right? There's a hot spot in southern New Mexico, but other places like the Great Plains have these huge mesoscale storm complexes because it's so big and flat, and you get these huge storm complexes. So they'll get a few weeks a year where these types of storms develop, and then they win. And the winner overall is the Congo. It's like the global lightning hotspot. Oh, wait, no. There's also this place in Brazil. There's like this lake in Brazil that is one of the biggest, it's a tiny little place, a few kilometers across, and it's like the world's biggest lightning density in this little place in Brazil. Japan, Indonesia's big for lightning. So in the United States, we are big, but there's these we call them hot spots all over the globe, and I think it has to do with the conditions for that convection.
Are there scientifically classifications of lightning? I mean, there's cloud and cloud ground, but you hear all these terms: dry lightning, fireball.